Hi, this is Ms. Cribb. I'm going to go briefly through the honors information on Chapter 13B. This is just an introduction, and I'm going to be using the Prezi, so I'm going to go ahead and make it full screen. And you can click through the Prezi, because really what I wanted you to do for this was kind of click through the Prezi and read through your notes. So you can look at your notes here, and it just says chemical bonds chemical bonds store energy. So you know that's true because food stores energy, and you eat it, the energy is released, and we use it. So when bonds are broken, energy is released. So that's what happens when we eat our food. Bonds are broken through vibration. So think about those intermolecular forces holding things together. They vibrate stronger. Well, that pulls molecules apart, but the forces that hold the actual atoms to each other have to be broken too. So the strength of a bond between any two atoms depends on the elements that are bonding and the length of the bond. Bonded atoms are more stable than unbonded ones. And energy is always required to break bonds. Kind of think about holding hands. Energy is always required to break them. You don't just let go, or people would have to push to open it up. So every time you have a bond between two atoms, you have to put in energy to break those atoms apart. Bond breaking is always endothermic then, because it always requires energy. And forming bonds is always exothermic. It always releases some energy. The stronger the bond, the more energy is released. Now, you could easily have read through this, but I'm just kind of talking you through it. A reaction that breaks strong bonds and forms a weak one requires energy. Think about that. Stronger bonds, if you're going from stronger bonds to weaker bonds, then the energy is going to be greater than zero, positive, endothermic. So let's listen to that again. A reaction that breaks strong bonds, that means you got to put a lot of energy in, but forms weak bonds. It only lets go of a little bit of energy. So you put way more energy in than you let go of, you're going to have a positive delta H. It's going to be endothermic. A reaction that breaks weak bonds, that means only takes a little bit of work to break it and form a strong one. If you form a strong bond, you release a lot of energy. That's going to be exothermic. And that's really a much more favorable situation. In most cases, exothermic processes are thermodynamically favorable. That just means it's more likely to happen automatically. And endothermic processes are thermodynamically unfavorable. Okay? Less likely to happen. Let's watch this video right here. Hopefully you'll be able to see it. Whoa, it didn't come up. Maybe, all right, we're going to keep going. I know it'll come up at some point. Endothermic reactions happen all the time. Ice melts, that absorbs energy. Compressed gas is released and gets colder, like when we use our Bunsen burners. Things are going from order to disorder, like your room, like my kitchen dishes. Order to disorder happens naturally. Okay? Chemical processes tend to proceed naturally in the direction that increases disorder. And the second law of thermodynamics relates this when it says that natural processes decrease the order found in the universe. Now, which has more order? Gas molecules, liquids, or solids? Well, think about it. Gas molecules are flying everywhere, so they don't have a lot of order. And liquids they can roll around each other. That's a little bit more orderly than gas, but solids are really kind of stuck, just vibrating in place. They have a lot of order. So that's the most order, that's the least order. Okay? Entropy, S, is a measure of randomness, or the lack of orderliness in a system. I like to say disorder. Listen to the S. Disorder. Entropy, S, is disorder. The more entropy, the more disorder. So which has more entropy? Gas molecules have more disorder, and solid molecules have less disorder. So entropy is disorder. The entropy of a substance increases with temperature. Well, that makes sense. The hotter it gets, the more likely it is to become a gas. It has more energy, it can fly around. At absolute zero, theoretically, all random movement of molecules would stop, and entropy would be zero. So you calculate entropy like you calculate enthalpy, which if you've watched the videos before, you knew. If you don't, enthalpy is just delta H equals the sum of the H of the products minus the sum of the H of the reactants. Well, entropy is delta S, disorder, that's the summation sign, the sum of the S of the products minus the sum of the S of the reactants. So put those in your notes.
Dr. Anderson, and this is Chemistry Essentials, video 57. It's on entropy, which is really the dispersal of matter and energy. So imagine I had a little bit of milk in a glass and I were to spill it. I will have increased the entropy of this isolated system. And there's an old saying that you shouldn't cry over spilled milk. I totally disagree with this. You should cry over spilled milk. And the reason why is it's an irreversible process. In other words, it's not just going to magically move back into the glass. You've increased the entropy and it's going to take a lot of work to put it back where it was. And so entropy in AP Chemistry is not something that you'll have to calculate. You have to understand it qualitatively. In other words, you have to look at a system and figure out what's happening to delta S. And so what is delta S? That's simply the change in entropy over time. Now, what does this little degree symbol stand for? That means that we're measuring it at standard temperature and pressure. And so if we were to look at a system, we should be able to make predictions about what's happening to our delta S. And that's what I hope you can do at the end of this. And so if we define it, it's simply dispersal. Dispersal of matter and dispersal of energy. So what are some examples of that? Let's say we were to make some phase changes. We were to go from a solid to a liquid to a gas. What would we be doing? We'd be dispersing or moving that matter away from its center point. And so we'd be increasing the entropy. In other words, our delta S would be a positive value. We'd make that matter dispersed over time. We also could do that by stoichiometry. In other words, if I look at the moles before a chemical reaction and the moles after, if I have more moles after the reaction, I've increased the entropy. And also, if we take a gas and we increase its volume, we're moving those molecules apart, and so we're increasing entropy, or delta S is going to be a positive value. Now let's say we look at energy. How could we disperse energy? Well, by increasing temperature. If we increase temperature of gas, according to the kinetic molecular theory, we're spreading that energy out and we're increasing entropy. Now, entropy is a term that people really struggle with, and so I wanted to start with a good example. And so I've got two videos here, but they're the same exact video. It's just that one of them is played forward and the other is played backward. And so your goal is to figure out which one is forward. So let me start playing that. It's just going to loop over and over and over again. And so your goal is to figure out which one is forward. Have you decided yet? The right answer is A, but that was kind of hard. Let's look at another one. I've got a little pendulum here, and let me play this video again. It's the same video clip. It's just that one of them is played forward, and the other is the same clip, it's just played backward. Have you figured out which one is forward? There's some clues in here, but the right answer is B. Let's look at the next one. It should be a little easier now. So if we look at the next one, I'm going to play this again. So again, same video, one's forward, one is backward. Hopefully you've figured this out. The right answer is B is being played forward, and A seems somewhat magical. It's being played in reverse. Let's look at the milk. So if we look at the milk right here, which one is being played forward? Hopefully you've figured this out. A is being played forward. Okay, and so why did I do that? Well, what we're looking at here are irreversible processes. In other words, if we play it in this direction, it's irreversible. In other words, it's impossible for it to occur in the reverse. Now, it's not totally impossible. That could occur, but it's statistically improbable that it's going to move in the other direction. And so that direction is really important when we start to talk about entropy, because what happens during an irreversible process is that we're increasing the entropy or the dispersal of that system. And it just doesn't move back, and that'll become really important as we talk about the next few videos. And so the second law of thermodynamics says that in an isolated system, or a closed system isolated from the universe, entropy never decreases. In other words, our delta S is always going to be positive. In other words, matter and energy are going to become dispersed over time. In other words, randomness increases over time. Now you might think to yourself, I know that's not true because I see stuff out there that's not random. In other words, I see trees and cars and DNA, and I know these things have a high amount of order. Well, you're not violating the second law of thermodynamics because remember, we're talking about an isolated system. And so we can decrease entropy in an isolated system, but as we do that, we're increasing entropy of the surroundings or the universe around it. And so again, to define entropy, what is it? It's simply matter dispersal, or matter.
Okay, that's really all I needed to know, wanted you to see there. I mostly wanted you to watch the increase in entropy, the positive delta S, especially of those blocks falling down. Okay, now you calculate the entropy again, the increase just like this, the sum of the products, the entropy of the products minus the sum of the entropy of the reactants. It's just an easy calculation, to be honest. A reaction with a positive delta S increases disorder, energy, and temperature. The products have more entropy than the reactants. Reactions with a negative delta S decrease disorder, and increase order. So decreasing disorder means to increase order. They would lower their energy and lower their temperature. Now, I've worked out all these example problems on a different tutorial, so I'm not going to do that right now. So all processes increase the entropy of the universe. That's what he just got through saying. A positive delta S means a reaction is more favorable. A negative delta S goes against this tendency and attempts to decrease entropy. All right. So we're not going to worry about all these different possible combinations of entropy and enthalpy. This one we've already had you watch before. We're going to just talk about Gibbs free energy. Willard Gibbs formulated a way of combining entropy and enthalpy. So enthalpy is the H and entropy is the S. Into Gibbs free energy, and it's delta G. At least that one makes sense. Gibbs free energy and delta G. And it's called delta G equals delta H, which is the change in enthalpy, minus the temperature in kelvins this time. Notice that, temperature in kelvins. And that's multiplied by the delta S, which is entropy. Delta G is a change in free energy. All right, if you get a negative delta G or a decline in the free energy, that signifies that a reaction might happen naturally or is spontaneous. A negative delta G gives you a spontaneous reaction. Negative delta G is spontaneous. A positive value is not spontaneous. Okay? And that brings us to, we don't need to do this because I made you watch that on Edpuzzle. And we're not going to worry about ways, this way to calculate delta G. We're just going to move to this one. That particular formula, delta G equals, that means Gibbs free energy is the delta H minus T delta S. This is the tutorial that you're going to watch on Edpuzzle in a different spot. And this one right here, I'm just going to allow you to go back to the Prezi and watch this if you want to on the delta G times delta H minus T delta S. This is more review on the Gibbs free energy formula. We're not going to go through it here. But Gibbs free energy, notice on this part of the Prezi, Gibbs free energy is the change kilojoules per mole. And then enthalpy is kilojoules per mole, temperature in kelvins, and the entropy is joules per Kelvin per mole. So you will have to do a little bit of unit conversions for this. So let's move forward. Let's skip the tutorial. Let's skip this particular one. Skip my tutorial, which is going to be on Edpuzzle, or you can watch it here as well. All the example problems are covered in the tutorial, and this is the assignment that you have. You can go back to the Prezi and watch this, and watch all the tutorials if you want to, but you need to be able to complete these questions and make sure you fully understand them before you take the test. And I will say that you can keep those in front of you when you take the test because it's an open note test even for you. Okay? Here's all the other tutorials I have out there on some of these concepts if you need to see them. And I'm not going to worry about all these. Let's just move on.
Hello.
And that'll be the end of this video, I'm pretty sure.
I'm wearing a hot pink shirt because
we're not going to care about his hot pink shirt. All right. So let me close this up, and I'll see you soon.